Question 3 has the following question about mass spectrometry. So here, the first question involves calculating the speed of an ion so that it can pass through the capacitor in a straight line. So the first thing to take into account are the two forces that it's going to feel. So first of all, there's an electric field due to the capacitor that is in the upward direction from the positive charge to the negative charge. It also feels a magnetic force due to the velocity that is perpendicular to the magnetic force, which will come into play in the calculation. First of all, the net force acting on the particle is zero, because that is what allows it to move in a straight line. Second of all, if we draw the particle, we can see that for the forces to cancel out, because one works in the upward direction, being the electric force, then an equal magnitude magnetic force has to act on it. So therefore, from this, we can write that the magnitude of the electric force is equal to the magnitude of the magnetic force. The electric force on the particle is due to the electric field, so the force is equal to the magnitude of the electric field times the charge, and the magnetic force is equal to the charge times the magnitude of the speed and the magnitude of the magnetic field, because the field is perpendicular to the speed, which is mentioned above in the problem as it is in the positive z direction and the velocity is in the positive x direction. So that's how you know that it makes a 90-degree angle. So instead of having to do a cross product, you can just deal with the magnitudes. Simplifying, you can cancel out the charge, as it does not matter in solving for this equation, and you get that the magnitude of the electric field is equal to the speed times the magnetic field. So from here, you can replace the electric field given that the voltage of the capacitor is equal to the magnitude of the electric field times the separation between the two plates. So rearranging this, you can solve that the voltage divided by the separation is equal to the magnitude of the electric field. So you can bring this back to the previous equation, and when replacing it, you get that the voltage over the separation is equal to the speed times the magnetic field. So this is easy to arrange and solve for the speed, which gives you that the speed is equal to the voltage over the magnetic field and the separation between the two. The second question then asks to calculate the mass of an ion given that you know the radius that it forms once it exits the capacitor region. So now the only force acting on it is the magnetic field, and it forms an arc of r, and with this curve pattern is due to the centripetal acceleration, which we can calculate as it is the speed squared over the radius of the curve it forms, and the force is obviously just mass times acceleration, which is due to the magnetic force, and that is just equal to, again, the charge times the magnitude of the speed times the magnitude of the magnetic field, because the two are perpendicular to each other. From this, the next step is to replace the acceleration with what we calculated above, which would be v squared over r, which gives you that is equal to the charge times the speed and magnetic field. From here, you can cancel out the two v's, well, one of the v's, and then it just involves rearranging for the m, since that's what the question asked for. So the mass is equal to the charge times the magnetic field times the radius divided by the speed. However, this is not the final answer, because the speed we actually calculated in the previous problem and needs to be replaced. So plugging in the previous answer, which is that v is equal to the voltage over b0 and s, gives us that the mass is now equal to the charge times b0 squared times r times s all over the voltage, which is our final answer for what the mass is equal to. Now, the final question asks for how you could identify the different masses of particles that are passed through here. Now, once the particles exit, again, they are only in a magnetic field. And this magnetic field, because of their speed, will cause them to curve according to the equation here that we calculated in part 2 of the question. So as we can see, if we look, the mass and the radius are actually linearly related. This means that as the mass gets bigger, so does r. So we would find a larger radius alongside a larger, more massive particle. So here we have a smaller black particle of mass small m, which will form a little radius of lowercase r. On the other hand, if we had a larger particle, so this gray particle, it would form a larger curve with a larger radius, big R, and it has a mass of big M. So that's how you could differentiate it based on the radius that it forms, or the distance it has from the capacitor.